So moving forward, now in any RAID where we are storing redundant copy of the data, such as what we are doing here in RAID 1, redundant mirrored copy of the same data twice, we would have problem of consistency. Let's say we are done, we got a logical write, we are done with updating this write to one of the disk, but while the RAID box was in the process of performing this write onto the second disk, there was a power failure. So it didn't went through successfully. What happens then? So RAID, such RAID mechanism that maintains redundant data will have problem of consistent update. What does it mean? Is the problem occurs in any multi-disk RAID system that has to update multiple disks during a single logical operation. For example, power loss between writes to disk 0 and 1 in RAID 1. So what do we do about this problem? Every time we have a problem, we have to solve the problem, right? How do we solve this problem? One of the approach to solve this problem is by using write-ahead log. Now, what write-ahead log does is it records what RAID is about to do, even before it does. So in the case of crash, the right thing will happen by running recovery procedures after that. So the recovery procedures can replay all the pending transaction that was about to happen to RAID, but didn't happen. So such a write-ahead log, if you can think, if you're already thinking that, well, if there is a power loss, wherever we are storing this, what RAID is about to do, even that will be lost, right? So we need to have an alternate redundancy for that component as well. So every time when we talk of redundancy, there's a redundancy in content and there is redundancy in time most of the time. And here what we are talking about is redundancy, not in terms of data, but redundancy in terms of an externally backed RAM. So wherever this write-ahead log is stored, it is battery-backed RAM. So high likely we can guarantee that even if the main power fails, but still then this battery-backed RAM will come into its action, and then in a way of using this battery-backed RAM, we'll be able to recover the data that was on its way and yet not returned to the RAID. Okay, so then let's discuss about RAID 4. Before we move to next RAID, I hope this performance metrics are of RAID 1 is clear to you, because there is a caveat in how we understand writes versus reads. And also there is a caveat between how we understand sequential reads versus random reads. Because when we have sequential reads, then consecutive blocks are not issued to the same disk. So that's the factor that makes this difference. And why do we have this denominator of 2? That's it. So then RAID 0 and RAID 1, they are the two simplest RAID algorithms. Now let's move forward to RAID 4. So in RAID 0, we saw that there is no reliability because there is no redundancy. In RAID 1, we saw that the redundancy is good, but we are losing a lot of capacity, like almost half of the capacity is just lost. So then RAID 4 came up with this solution to save the capacity at the cost of performance. So here in RAID 4, we are saving space with parity. But there is always a cost for any benefit, right? Especially in system. There's always a cost benefit analysis, and almost equal to null chances for just having a benefit without any cost. So here the space is traded at the cost of performance. We use the word parity over here. We wouldn't be going in depth into what are the different mechanisms to calculate parity, but so just to ensure that you're not alien to that word of parity, because then you would not understand RAID 4. The simplest form of parity could be XOR gate. Now, I hope everybody is familiar with gates, NAND, NOR, XOR, OR, and all this. Basically, if we are to write the table for XOR gate, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. That's the XOR gate table. Where if we have two ones, that leads to 0. Like any two similar digits always leads to 0. Any two different digits would lead to 1. So if we have, now how do we use this logic of XOR, like logic of parity, to design RAID 4? So in RAID 4, if we have 4 disks, let's say if we have 5 disks, or let's just stick with our example of 4 disks. In that case, we would have 3 bits. Okay, if we want to divide things even out, so we would need an extra disk as well. So let's say if we have 5 disks, then while writing, we have blocks, and let's say if you're writing in the granularity of bits, then we have our bits spread it out in the sense first, second, like this. If we have things stored like this, now where do we store the parity? Question mark, right? We cannot store the parity. So let's go back. So we would have to reserve 1 disk for the parity. That's exactly what we do in RAID 4, and that's where we need this extra disk. So we store the data, and then we store the parity for this row of content over here, P1. Then we store the data, 4, 5, 6, 7. We store the parity for that row of content here, and so on and so forth. This is how we organize data in RAID 4. Now, how do we calculate the parity is by using XOR logic over here. that we discussed. So depending on, let's say if the content stored here in this block could be represented as 0 and 1, we can have something like 0, 0, 1, 1. What we do is we count. Let's make some space to write here. So we count number of ones including parity bit. And this number must be even. Even this is how we can compute, and even we can reconstruct. The good thing about XOR is even the reconstruction can be done by using just the same XOR logic. So let's say in this example, while we are storing, I'll use different, yeah, let me use different color. So in this example, while we are storing 0011, the parity bit, what will be the parity bit? 0, because it's just an XOR of these 4 bits with this logic over here. If there are even number of zeros and even number of ones, then XOR of that will be 0. Then let's say if we lost this disk, so we lost the data over here, how do we reconstruct? We would just look at the remaining data wherever we have, including parity bits. So we have 0, 0, then we have 0, and we have 1. So in order to make even number of ones, because our parity bit is 0, we need to have one more 1. That's definitely one of the logic. But also if you just compute an XOR of 0, 1, 0, 0, 1, and 0, what is the XOR of that? 1, right? Because we have, according to these two content over here, for any odd number of ones, the XOR is 1. So that's the best thing about XOR, that we can also reconstruct by using XOR. So now if we have to store bits across our disk, then we are pretty sorted out. It should be very clear. Now you must be thinking, what happens when we have bytes? Because the granularity at which we store IOs into our disk is blocks, and a block can be something like 4 bytes. So how do we deal with constructing RAID 4, where we have to, now we cannot store just single bit by bit, but we have to store the data at the granularity of 4 bytes. Well, again, we could divide this 4 byte into bits. Yes, there'll be many, many bits, but we can have that string of bits for each disk, right? Now, let's say rather than 4 byte, let's take a smaller example that we could digest and understand. Let's say that our block size is 2 bits, still greater than a single bit, but something more. So then we would have, instead of just a single bit, we would have 2 figures where we could say like 0, 0, 0, 1, 1, 0, 1, 1, something like that. So if we have 2 bits for each disk, if it's a 4 byte, we just have some more bits for each disk. What we could do is we would still have the parity of exactly the same number of bits. In this case, if it's 2 bits, we would have 2-bit parity. If it's 4 bytes, then we would have accordingly that many bits for parity. And when we compute the XOR logic, we do not need to worry about the whole 4 bytes. That's the best thing. We can just do it a bitwise XOR. So we can just do XOR for the first bit to compute the first parity bit, and so on and so forth. So a bitwise XOR for each bit of data which is again in the binary version, is good enough for whatever is our block size. We could work with that. So now that we understand how do we store data in RAID 4, still easy, not as straightforward as RAID 0 and RAID 1, but it seems more efficient, right? Let's put this, seems more efficient. Let's put some quantities to that. Let's quantify that. So let's do our analysis. Okay, so in terms of capacity, now why should you always get a chance to work on just the performance by yourself? Let's also take an opportunity to work on capacity by yourself, right? This time. So for RAID 1, what is the capacity that we are utilizing? So if we have n disks, here we had 5 disks, we are using 4 out of 5 in an efficient way, right? But this disk 4, is just storing parity. It's not storing user data. That's why for capacity, we have n minus 1 multiplied by b, because 1 disk for parity. For reliability, how many disk failures can RAID 4 tolerate? 1, yes, definitely it can tolerate 1 disk failure, because we saw here in this example, right, where disk 2 fails and we reconstruct its data by using the parity data. Can it tolerate, in this example, can it tolerate 2 disk failures? No, it cannot. So if disk 2 and disk 3 fails, then we would have no way how to reconstruct the data for both this disk. We wouldn't know exactly what data is it. So reliability, we can tolerate exactly 1 disk failure for 1 RAID 4 group, for which we are maintaining a single parity disk. What happens in terms of performance? So when we talk of performance in terms of throughput, we have sequential read, sequential write, random read, random write. Start thinking what happens, what is the performance for each of this?